All right, you are welcome to our practical session on optics for alternative B, Waec 2024. Optics, alternative B, Waec 2024. Okay, this is my speculation. The question is on the paper with the diagram as we're going to set it up. Yeah, so you can see the question. There from the question, this is the table, the reading. This is how the reading table will be. You have column for D in cm, you have D squared, you have L1, you have L2, you have L, you have L squared, you have D. D is a function of L squared minus, a function of D equals D, small d squared minus L squared. Capital L is a function of L1 minus L2. L1 is image position, first image position, that is V. L2 is the second image position, which is TV. Then D is the distance between the screen and the object. The object here is the ray bus. Then these are the distance separating the ray bus, that is the object, and the screen where the image is formed. So we'll be stating two precautions. I avoided error due to parallax while taking them from the meter rule. Then, well, you should know what is the difference between a virtual image and a real image. A virtual image cannot be captured on the screen, but a real image can be captured on the screen. So if you're asked to explain what it meant for the focal length of a lens to be 25 cm or 15 cm or 10 cm, how do you explain that? It simply means that the distance between the principal focus and the center of the mirror is 15 or 10 cm or 25 cm. So we want to go and do the needful as we set up the apparatus. That's the question once again. And remember, my name is Amechi Peter. My YouTube handle is at Peter, Pita, Amechi, Amaech at 2028. Okay, let us set up the apparatus as we proceed. Okay, here we are. This is the ray bus. You can see it is on. There is a bulb inside the ray bus. This is the lens, that is a converging lens, or what we could call a convex lens. So convex converging lens, that's the lens. This is the lens holder. So I use this as a support to raise the lens holder because my pinhole of the ray bus is higher. So if I keep my lens with the lens holder on the table, the ray from the object might go overboard and it might not give me the expected sharp image on the screen. This is my screen, so this is the setup as seen on that diagram. So this is the ray bus, this is the meter rule, this is the lens, the black one is the lens holder, this is the screen. You can take any color. This is white screen, it can be a black one. So that is the overview. You can see I'm using an electrical socket to power the ray bus. So the first from the instruction is that, as seen, Fix the meter rule. We have done that. Place the illuminated object on zero end. You can see zero end of the meter rule. The object is there. Then so that the distance between the illuminated object and the screen is 100 cm. So the meter rule is 100 cm. 0, 100. So my screen is taking the 100 cm, 99, after 99, 100. So the distance between the two is actually 100. So what the next thing we do, record the distance as 100, D. We have recorded it, D. Then also evaluate D square. So using your calculator, square of 100, you put the value here. Then place and move the converging lens between the illuminated object and the screen until a sharp image, diminished image is formed on the screen. So the first assignment starts. You move. This is the screen. So let's see when we get a sharp image of the object. It's appearing gradually. You can see. Wow. You can see. You see that dot? This is from the pinhole. You can see this big circle appearing diminished. Very sharp dot. You can see that. That is sharpest. If you go more, it becomes more blurred. The image becomes broadened. A blurry image, you take it back because that is not a sharp. Take it back to get a sharp appearance. Adjust it back and forth. So you can see that is a sharp appearance of the image on the screen. Then you measure the distance. Measure the distance on the meter rule from the middle of the lens holder. You get 81. Remember, from here to there is 100, so you move from there. So this is 81. 81 from 0. 81 minus 0 will give us 81. That is L1. So we record L1 81.000 in 3 decimal placement. Then we repeat the same procedure. We have recorded it as L1. Then we repeat the same procedure. Now move the lens towards the object until another sharp image is formed on the screen. Read and record the new position as L2. Now we move backwards to form this image. The next thing to form this sharp image, as you can see, that is our L1. Distance between the ray boss, that is the object, and the lens, that is L1. To form this sharp image. Then we move it front now, forward towards the object. This is our object. To form another sharp image. So you move. You can see our screen. The image is disappearing. We are moving front to the forward towards the object. Look at the screen. Something is happening on the screen. You can see the screen. You can see an image on the screen. You can see another image has been formed, a sharp image of the wire gauze formed on the screen. You can see the image here. The image is formed there. You can see the image, sharp image of the wire gauze. Yes, that is the second image formed. You check the distance where that happened from the midpoint of the lens holder. That's 17. 17 minus 0 is 17. So L2, you record accordingly on your table. L2 is 17.00. Then L will now be 81 minus 17. L square will now be the value of the difference. That is the value of L squared. Then D will now be D squared, that 100 squared, minus the L squared. Remember how you get L squared? The value of L squared, the difference between 18 and 17, the square of it is what you now do to get L, the D. So you repeat the process. The second one, the distance, 85. So you adjust the screen from 99 to 85. You can see the new position of the screen. That is 85. So an overview, that the whole display. You adjust again. You adjust to get a sharp image by going back. That's L1. Look at the image. A sharp image is being formed. You can see that dot diminished. L1 is diminished, but L2, when you are going forward to meet the object, the image is enlarged. So you check where you have a sharp image as you move back and forth. So that the sharpest, you take your reading from the middle of the lens holder, that is 64.5 on the meter rule. You record it, 64.500. Then L2, you go forward. You are moving forward. As you are moving forward, image is appearing. Yes, we are there. You can see the screen. That's the image. Another precaution is you ensure that you are in a dark room, because we don't need too much illumination in this type of experiment. Why? Because we are producing light, so we don't need light again. So we need darkness to appreciate that light. So this is the second image. L2 now, you check the distance from the mid value, 17. It's a coincidence. 17. You now do 64.5 minus 17. As L, you square the value. Then D squared, square of 85, minus L squared. That is the second round. The third, you repeat the same procedure. You adjust the new position to 75. You adjust your screen, the distance between the screen and the ray bus, 75, and you repeat the same procedure to get a sharp image on your screen. And the procedure continues. So remember, it's interesting. At the end of the day, we are to plot a graph. We are to plot a graph of L squared against D. L squared will be on the vertical axis and D will be on the horizontal axis. With that, there is no how you will not make A1. Thank you for your time.